a new topic for you regulars at come. So yeah, I'll be talking about clouds in the troposphere and they're basically the regulation of climate. I have three sections to the talk. And the first one is just going to be very simple, fun, mainly to get our kind of our mental juices percolating here, to learn or at least remember some things that we may have known or maybe do know right now about cloud basics. So things like, what are clouds made of? How do they form? Why are they white and how prevalent are they? God, if I forget to mention here, I've got some images scattered about through the presentation, so if you start to nod off, you'll have something pretty to look at. So I may not talk specifically about all of them, they're just really there for eye candy. What are clouds made of? Condensed water vapor. We'll start with the easiest one. I think most everyone knows that. Kind of similar to this process, you can see the condensation on the exterior of this cold glass from the ice cubes. Condensed water vapor there. We know the temperature at which water vapor will condense is known as the dew point. And we also know that when the dew point is equal to the air temperature, the relative humidity is 100%. How are clouds formed? A lot of us, myself included, thought we knew how this works. So looks like I'm kind of got a little bit of a resolution image. Is it fine? Okay, sorry that's cut off and left here. If we want to know how clouds are formed, we actually have to know a little bit more about the dew point temperature. What I'm showing here is a plot, and this y-axis is decreasing temperature as you go up. The x-axis is the rate at which water drops arrive at a surface, the condensation rate in black, or leave a surface, the evaporation rate in red. What maybe is not very accurately understood is that water molecules are constantly moving back and forth between the three phases, gas, liquid, and solid. That's irrespective of what's going on in the air around the water vapor. As the temperature decreases, there's a point, this dew point temperature, where the condensation rate will exceed the evaporation rate. It's at that point that there can be net condensation and the cloud can form. I won't say it will form at this point because it depends on one more variable. The slope of these curves depends on the vapor pressure of the substance of water vapor. And so this is just my rendition. In the bottom here, what I've denoted as cloud-free air is basically not entirely true. It's just that the cloud particles that are forming and evaporating are subvisible, and they don't stay around for very long. They evaporate too quickly for our eyes to see. When a cloud will form, we have to add one more thing in, and that's something we call cloud condensation nuclei. At the atmospheric temperatures and humidities that we have in the lower Earth, we need to actually have a substrate to allow that water to transition from gas to liquid. And that's called cloud condensation nuclei. It's really very small dust particles or sea salt spray, things like that. I should probably mention there are several common ways to allow an air parcel to cool in the lower Earth atmosphere, and those include buoyant lifting. This is what we would commonly call convection. We have it all the time here in the summer months. Air is heating up, radiation is heating up the air near the surface. Air rises, and you get these puffy cumulus clouds in the mid-afternoon. We can also have topographic lifting, where air is forced up over a boundary, like the Flatiron's just to the west. And finally, you can have convergence of air, such as a warm front and a cold front meeting, and the warm front is forced up and over the cold front. Those are three typical ways that you get temperatures to decrease in the atmosphere. So we've talked about that clouds are composed of condensed water vapor, water droplets. So my question is, why do they float? Here is a picture of a water droplet descending as we would expect under the force of gravity. And here's a nice picture of a cumulus cloud floating in the sky. And the answer is really that they just appear to float. There's a lot going on in there that our eyes just don't see. For example, the fall velocities of the cloud droplets, which are very, very tiny particles, is so small. The fall velocity, you can think of it as a balance between gravity force and a drag on the particle. Updraft velocities, the convective air motions in the cloud, even if they're, it's not a precipitation-inducing cloud, so small updraft velocities, they can still be 1,000 times the rate of any downward motion in the cloud. So there is actually droplets descending in the cloud. They're being pushed up. The droplets that make it out through the base of the cloud encounter a temperature that's warmer than that critical dew point temperature. So they evaporate from view, and we no longer see them. So it gives the appearance that the cloud is staying stationary there. But really, they're far from stationary. Clouds, when the updraft velocities die out, the clouds are going to dissipate, and they reform. And they do this really all the time. Some fun facts. Clouds have billions of tiny water droplets in them. If you took a typical cloud and measured the mass of the water in all those droplets, don't be surprised if it's several hundred kilograms to several tons or even more of mass of water in that cloud. And just for perspective, 200 cloud droplets, say about thereabouts, could fit on the head of a pin. And that would be 20,000 cloud condensation nuclei on that same pin. And these are very tiny. Why are clouds white? This is a common question here. The answer has to do with scattering. I'm sorry about the resolution here. What we have to do, what's going on here is the interaction of the incoming light with the cloud particles. If that light was to impinge on a single particle, the key parameters determining that the scattering properties would be dependent on the size of the particle and really the wavelength of the incoming light. So as we have different particle sizes and light of different wavelengths, these the angular distributions of the scattering can be quite different. However, when you have multiple scattering, is what would occur in a cloud. Light comes in, bounces off one particle, then the next, and the next, and the next. You do that enough, you remove all of the angular and wavelength dependency to that scattered light. And no matter the distribution of the particle size, small particle or large particle, what you get is a white cloud. If you look at the picture here, you'll see some gray areas. That's really just shadows. It's shadows from the cloud itself, or even an overlying cloud from up above. If you were to be an observer, say, on an aircraft above this cloud, it would all look white, just as you would expect. It's also fun to realize that multiple scattering is also the reason why milk is white. Milk, the fat droplets in milk, and cloud droplets are not the same size. You would expect a different scattering response from these because they are different particle size. Yet once you add some multiple scattering to the mix, you're going to get white anyways. You could do a little experiment for yourself, or just take a couple drops of milk, put it in a glass of water, and look at the scattered light from that. And your result is going to be a lot more like the blue sky than the white of the clouds in the milk. All right, global cloud coverage. This here is a picture of the Earth from space. See these white regions of clouds here. This here is latitude versus longitude. This is a collection, database collection called International Satellite Cloud Climatology Project, or ISCIP. And what we're showing is that an annual mean cloud cover averaged over 19 years from the early 80s to 2008. Red areas are essentially little to no cloud cover, and the lightest of the blue colors are essentially persistent permanent cloud cover. we can look at a plot like this and, go ahead.
Is this strictly daytime clouds, or do you have some way of measuring night clouds?
You know, that's actually a really good question. The databases that I know that contribute into the satellite cloud climatology project, I'm usually thinking about the cloud retrievals from the shortwave instruments. So this would require having some sunlight on the scene. I do not know, actually. I'll have to look into that and let you know if there's some sort of nighttime infrared retrieval of cloud quantities. No. It's all daytime. Cloud expert in the back there, so. Thanks, Peter. Yeah, that's a good question. I didn't know the answer to that one. We can learn a lot, actually, well, let me back up a bit. Knowing that clouds are tied to the rising motions, the dynamics of the atmosphere, we can actually tell a lot about some typical dynamical motions in the lower Earth atmosphere from this plot. And also we can learn more as well about moisture content, the atmospheric composition. For example, if you take a look at this red region here, that's right over the Sahara Desert. It's extremely dry. Antarctica here, also very little amounts of water vapor. This region right here is something called the equatorial warm pool. It's a region dominated by pretty persistent subsidence. This is downward air motion that's inhibiting cloud formation, which requires an upward air motion. You can see in general that oceans tend to be far cloudier than land. And tends to be a very distinct band of near persistent cloudiness right around the equator called the intertropical convergence zone. And this is a region where surface air from the north and south hemispheres are converging together, forcing tend to be an uprising at that point. If you were to take a global average of this, at any one time you find that 67% thereabouts of the Earth is covered by clouds. It actually raises a question. There's kind of a rule of thumb. If you can imagine at any one time, half the air in the atmosphere is rising and half the air is sinking. You would expect only about 50% clouds. That extra 20% that's in that value is what's known as tropical cirrus. These are really persistent, high altitude ice clouds that are very thin, not visible to our eye. This result wasn't attainable until the satellite era. Okay, clouds and climate. So we had our fun with some basics. You know, this is where things are really going to get interesting, I think. I hope you enjoy it. If we're going to talk about climate, we actually have to know what weather is. And if we want to talk about climate change, we have to know what climate is. So we're going to define those. We're also going to look at how energy flows in the atmosphere and how clouds affect this energy flow. Clouds tend to be called they have a dual effect on this atmospheric flow, which is commonly called the albedo effect in one case, and a greenhouse effect on the other. And I'll define these terms more and get into them later. We'll also take a look at how sensitive is Earth's climate to clouds, and take a short historical view of the treatment of clouds and cloud feedback effects in climate models. We're going to use some back-of-the-envelope calculations, real simple calculations that I think will give you a lot of insight into these processes. So here we have weather and climate. Weather is really just the instantaneous conditions of the place. Look outside, that's what you have as weather. Climate is the average of weather. It's averaged over time and space. Climate change is long-term changes in weather patterns. That could mean average conditions, distribution of the weather patterns, or even the number of extreme weather events. And it occurs over long time scales, decades, even to millions of years. One caveat, if you're hearing about climate change in the context of environmental policy, we're actually looking at a change in modern climate that's induced by humans. So this is a cartoon showing some of the energy flows in Earth's atmosphere. There are similar cartoons like that, like this, that have climate scientists have really devoted their careers to assigning values to each entry on here. And I found it kind of complicated for just a real overview. So I left the numbers off. We're going to actually derive some of the numbers ourselves. For example, if we take a look in the purples here, this is the what we call the solar energy, sometimes called short wave. This solar energy that comes in, it can be scattered by the air, reflected by clouds, it can be absorbed in the atmosphere, absorbed by the earth, and reflected by the earth. If we look at the long wave, this is the what we would call the infrared radiation. It's the radiation that we cannot see. It's sometimes referred to as terrestrial as well. This infrared radiation can also be absorbed within the atmosphere and emitted by the atmosphere or clouds, or escape all the way to space. When the total incoming and the total outgoing are equivalent to each other over long time scales and large regions of the whole Earth, that's what occurred to as which is, called radiative balance. At any one time in a little region, you're never in radiative balance, and actually it is that imbalance that drives the atmospheric motions. Okay. Clouds have a dual effect on the energy flows in our atmosphere. Commonly referred to as the albedo effect and the greenhouse effect. Let's concentrate first here on the left-hand side of the albedo effect. What this means, let me back up a little, just make sure I have the time to find albedo. Albedo means the fraction of incident solar light that's reflected back up to space. So if you have incoming solar energy, say it strikes a cloud here. This is a relatively thick cloud. These tend to be lower in the atmosphere and fairly warm, meaning that they're relatively near the same temperature as the Earth's surface. These tend to have a high albedo, meaning that they scatter a large portion of their incoming radiation back to space. Some of it does get through, can be absorbed at the Earth's surface and emitted, and then absorbed in the cloud and emitted back down to the Earth. That's the infrared portion right there in the red. These low clouds that are relatively at the same temperature as the Earth's surface have a strong infrared emission, meaning that relatively little of they add relatively little extra infrared radiation into the atmosphere. So in general, for the albedo effect, this portion here of the plot dominates, and there's a net cooling. The greenhouse effect is really the opposite. This is what occurs when you tend to have a...
Are those stratocumulus clouds the low, thick, warm ones?
You could call them that. You know, really, it doesn't really matter what you call them, but more their property. So these tend to be a thicker cloud and a warmer cloud. Doesn't necessarily have to be stratocumulus, it could just be cumulus.
Cumulus, yeah, puffy,
Yeah.
puffy cloud.
Right, and this high cloud, what they're calling high clouds here, maybe more commonly, or a common example, that could be cirrus.
Right, what I thought. Great, thank you.
You're welcome. So, in the greenhouse effect, which, by the way, is a really terrible name for this this whole procedure here, and I'll explain why later. But it's pretty commonly used, so we're kind of stuck with it. These high clouds are cold and they tend to be quite thin. They don't block very much of the solar radiation come through, so most of that comes down, warms the Earth's surface. Now there is a little bit that's reflected back to space, but not as much as in this case here. You can tell by the width of the arrows. The infrared radiation here that's absorbed by the Earth and then emitted in the form of infrared can be absorbed by the clouds. Some goes back to space. Some is directed back towards the Earth's surface, increasing the...
What is the source of the infrared emission, particularly that strong one? Is that reflected energy from the albedo effect?
It's not reflected. This is energy that has been absorbed at the Earth's surface or in the cloud and emitted. When you have a large temperature difference between the Earth's surface and the cold temperatures of this cloud top, you can get a much larger net effect from the infrared radiation in that atmospheric layer. That's why they tend to call this side of the graph the greenhouse effect. And in general, it causes more of a warming by adding more energy here. Oh, one more detail. If it's nighttime and there's no sunlight, both of these cases, all clouds will warm at night. Okay, let's talk a little bit more in depth about the albedo effect. What we're showing here is the satellite image of Earth, including all the clouds. On general, its albedo is 30%. That means 30% of the incoming incident solar radiation returns to space. This is some rendition of the Earth without clouds. The albedo of the Earth without clouds is about 15%, half that with clouds. So they know that clouds approximately double the albedo. That means double the energy per unit area that is reflected back to space in the presence of clouds occurs that wouldn't in their absence. You can do a fun little calculation here. This is the first one of our back-of-the-envelope calculations. This might be where some of the issue comes in. We've already learned in the talk that the typical cloudy sky fraction of Earth is about 67, just say 70%. We know Earth's albedo is 30%. Just as clear, if it was no clouds, only clear sky, it'd be 15%. So if we wanted to determine the albedo of only the average albedo of just the cloudy areas here, we have to say that this total albedo would be equal to the fraction of the cloudy sky times by the cloudy sky albedo, which is what we want to know, plus the fraction that's not cloudy multiplied by the clear sky albedo. So here, what we get is roughly 40%. I guess just as a comparison, the albedo of the moon is 10% or less. Okay, clouds and the greenhouse effect. There's lots of definitions of the greenhouse effect that you can come across, and they may give you the right answer but for the wrong reason. The definition that won't get you into any trouble is just considering this. There are two sources of energy incident on Earth's surface. The sun is one, and the atmosphere is the other. The atmospheric contribution is the greenhouse effect. Okay? It's neither a trap or a blanket, and it operates nothing at all like a greenhouse on Earth. So, this atmospheric contribution comes in the form of infrared radiation that is directed towards the Earth's surface. Clouds are the major non-gas contributor of that infrared radiation directed towards the surface. The primary greenhouse gases in our atmosphere, in order of importance, are listed here. Water vapor is the most important, followed by carbon dioxide, methane, ozone, and nitrous oxide. All of those gases comprise less than 1% of the atmospheric composition. So what it means here is that less than 1% of the atmosphere can contribute infrared radiation directed towards the Earth.
Yes, the infrared radiation from a cloud would be equal up and down.
Not necessarily, no.
Pardon me?
It really depends on your, you should go back.
The original source and thickness.
Take a look back here. This, yeah, exactly, thickness, composition, to really tell you about all those details, but temperatures, the big gas in the atmosphere is a greenhouse gas? If you have any diatomic molecule, that means a molecule that's composed of two atoms, and they're not the same atom, it's radiatively active. That means it will direct infrared radiation towards the Earth. Any molecule that has 3 or more atoms in it is radiatively active. All of these guys here have 3 or more atoms. Let's revisit this plot that I showed earlier, and we're going to do some calculations and put some numbers on it. What we're going to learn from it is the net effect of basically which one wins, albedo effect or greenhouse effect. What is the net effect of clouds on the current climate? But we know that satellites tell us that clouds approximately double the albedo from the Earth from 15 to 30%. So if we want to know how much, look at the albedo effect here, we want to know how much sunlight is going to be reflected back to space before it even interacts in our atmosphere. We have to know how much sunlight is coming in. We actually know that very well, thanks to Ray Kopp here at LASP. If anyone came to last month's public lecture, Ray Kopp gave that, discussing his measurements of solar irradiance from the sun. You probably noticed that his value was different than this one here. The total solar irradiance at the top of the atmosphere is around roughly 1361 watts per square meter. I'm going to be using this term of basically energy per unit area watt. This value is 1/4 of that because I'm accounting for a global average. If we multiply this value by 15%, we're going to get 50 watts per square meter. That energy is what is being sent right in, that's a fraction of the incident that's being sent right back to space. 50 watts doesn't sound like much. This is a 50-watt light bulb. Not too impressive, that doesn't seem like much. However, we really have to account for the per square meter here. If you calculate the surface area of the Earth, 50 watts per square meter would be 130 trillion of those light bulbs. It's a lot of, that's a big number. We also know that satellites tell us that roughly 30 watts per square meter is contributed by clouds to the greenhouse effect, the infrared radiation warming that would occur in their absence. So if you do a simple comparison of these numbers, you'll see that the net effect of clouds on our current climate is one of cooling by approximately 20 watts per square meter. What if we wanted to know the portion of the greenhouse effect that's due to clouds alone? We'd first need to know what is the energy per square area that's added just by the greenhouse effect. And then knowing that the cloud contribution is 30 watts per square meter, we could determine what portion of that is of the total. Looks like I'm missing some. Here we go. We can estimate this really quite effectively, knowing 3 things. We know the average surface temperature of the Earth. That's 288 Kelvin, roughly 15 degrees Celsius. I can't think what that would be in Fahrenheit. We can also actually compute the temperature, what the temperature of the Earth would be without an atmosphere. That's 255 Kelvin. That's minus 18 degrees Celsius. Very chilly. Right there it tells you why the greenhouse effect, as we call it, is so good. It's a good thing. Now, we could also, using Stefan Boltzmann's law, compute the radiation that's emitted from a body is going to be proportional to temperature to the 4th power. And I say ideal black body here because it's a theoretical construct, but it's going to be pretty accurate for our purposes. So, we could set this calculation here. This F is going to be our total greenhouse effect, which is basically the addition of infrared radiation from the atmosphere towards the surface. It's going to be this calculation here. The sigma is the Stefan Boltzmann parameter. Here's the temperature of the surface, Earth's surface to the 4th power. Here's the temperature of the Earth if there was no atmosphere to the 4th power. We get approximately 150 watts per square meter. That there is the greenhouse effect. It's really quite startling if you think that this number is almost half the global average incident energy from the sun. It's a lot. If we look at the cloud contribution, it's a modest 20% of that total. So I spent a lot of time talking about clouds and current climate. What if we wanted to look, for example, at how clouds are going to respond to a change in climate? I wanted to start with a fun question here. I'm going to say this statement, but I'm going to ask for some audience participation. Because clouds cool the present climate, they will act to moderate global warming. Could I ask for a show of hands? Who thinks that is true? Okay. Who thinks it's not true? And it's really not a test. It's really just for fun. So, anyone think that's not true? Who thinks unable to say? The vast majority of people. Turns out pretty intelligent audience here. Yeah. The C, believe it or not, is the correct answer. Obviously, we would like to be able to say it's yes or no. We can't yet. So the next session of my talk is going to be really the reason why we can. What we do know compared to what we don't know. What we really are asking is what is climate sensitivity? This means what is the measure of the response of Earth's temperature to a change in radiative forcing or a change in cloud properties? We're not asking what is Earth's temperature to the current cloud. We want to know how is it going to respond to a change in those cloud properties. It can be represented by what looks to be a very simplistic equation. Delta T here is a change in temperature equals this variable lambda. That's one that's typically used for climate sensitivity parameter. And F here is the forcing, change in forcing. You could simply solve this for this lambda. But that lambda has a lot in it. It really is representing the full complexity and interrelations of the Earth climate system. When people are trying to do this in a climate model, it's not just model physics, but it's also model parameters that could be tuned. So it's maybe a simple construct, but it's difficult to do in practice. A benchmark measure of climate sensitivity that you may have heard about in the news is the radiative forcing associated with a doubling of carbon dioxide in the atmosphere. That's quoted to be about plus 4 watts per square meter. And the temperature change expected for that kind of radiative forcing is a 3-degree increase in temperature. Just a reminder that a doubling of carbon dioxide gas is, please don't confuse that with current estimates of greenhouse gas forcing, which is around 2.4 watts per square meter. So let's do another back of the envelope calculation. We're going to try to understand the interrelationship. How is there a sensitivity of clouds to climate? I'm going to start off by making another statement. I'm going to assume that cloud albedo is sensitive to surface temperature, such that if there's an increase in surface temperature, it's going to increase the albedo of the cloud. By what percentage would we need to increase that cloud albedo to offset a forcing that you would expect from a doubled carbon dioxide environment, about 4 watts per square meter? Well, we can set this equation here. We can say our change in net radiation, which is going to be this 4 watts per square meter, has to be equal to the incoming radiation times the portion of the sky that's cloudy, 67 roughly %, times by the change in cloud albedo. Just do a little rearrangement here, solve for this factor. And you're going to get what seems to be quite a small number. Cloudy sky albedo would need to increase by 0.0175. It's around 5% of the present value. If you take a look at these series of pictures here, you can see, even just by your eye, there's much larger variability in there than 5%. Now that sounds possible, but let's take a look at this number. Remember this number number in your head, 0.0175. And let's actually just take a look at what a couple different estimates of the global Earth albedo suggest is the variability in global Earth albedo. This is not just clouds, this is clouds, surface, aerosols, contribution to the whole system. What I'm showing here is a plot of time. This is 2000 to roughly 2004. On the right-hand axis is the albedo anomaly, such that positive values mean an increase in albedo, hence a cooling effect, because there's an increase fraction of incident solar radiation that comes back to space. The left-hand axis is the what they call shortwave flux anomaly. Negative values then would be a warming. Ignore for a minute that these two estimates are in stark contrast to each other and have what appears to be opposing trends. You take a look at that number, 0.0175, you can see that that's not even close to what is currently suggested of the variability in the global Earth. So there's no indication that Earth's global albedo varies remotely near to what we would need to offset a 4 watt per square meter warming. Let's talk a little bit more about the data in this plot. The blue line is satellite data of Earth's albedo. The orange boxes here are something called Earthshine. This is when sunlight has been reflected from the Earth to the moon and then reflected off the moon back to Earth. It's a double reflection. It's a very, meaning the reflected light in that case after double reflection is quite dim. And the satellite data is suggesting essentially little or no change in Earth's albedo. They think it's natural variability across this time series. The Earthshine data is suggesting that these values about a 6% increase in global albedo over that same time scale. If we, maybe before I go on, even before showing anything else, one of the take-home messages from this plot is that what appears to be seemingly small changes in global albedo have very large impacts on radiation. Okay? If we say, for example, that we're going to say that the Earthshine data is correct, there's been an increase in albedo to this extent, have we seen some sort of global cooling as a result over that time period? I don't show the results on here, but this amount of albedo anomaly is double or more what occurred after the Mount Pinatubo volcano exploded in 1991 and ejected gazillion amounts of aerosols into the stratosphere, largely increasing the reflection of the radiance back to space. And there was a measurable 2-degree cooling globally averaged within 2 years from that volcano event. And there's been no detectable trend in surface temperature or in the ocean heat content, which is a measure of the energy stored in the ocean during that time. Wanted to place an arrow on this plot just to kind of emphasize the importance of improving our ability to measure global albedo accurately. The differences between these two albedo estimates actually exceed what's currently expected to be the greenhouse gas force, 2.4 watts per square meter. The Earthshine people very recently, 2008, published new results. I don't quite know all the details, but they installed a new telescope at their observatory, recalibrated their old data, came up with some somewhat reduced values here, but they're still showing a positive trend during that time. One thing that we should investigate this time, because we do know that clouds have this dual role in climate, that they can increase albedo, but they also can increase the warming of the atmosphere through the albedo and their greenhouse effect. So we could take a look at some other results and change in cloud cover that could mask a cooling that's suggested by the Earthshine data? And the answer, I think, would be quite surprising, or not surprising, but intriguing. Regionally and seasonally, the variability in the reflected energy from clouds is far, far greater than 4 watts per square meter. If you take an annual global mean of that, you're going to get something around half a watt per square meter. This implies that the variability in cloud cover is small, less than 1%. If you take another look at this ISCIP data, when I said the global average of that was 67%, if we did this again next year, it'd be roughly 67%, and the year after that. Well, that is, maybe I should go back in time. So, excuse me, so, I'd also like to mention if we went back and took a look at this plot, a half a watt per square meter would be roughly, they put a dash line in here, but they expect the variation in albedo is roughly in that range. These values that are outside of that is probably predominantly instrumental noise sampling issues, basically just a call that we need better and longer term measurements. So let's see here. Okay. Aha. It would probably be amiss if I gave a lecture and didn't discuss the feedback effects of clouds. And I'll tell you a little bit in a bit what actually we mean by feedbacks. I told you earlier that the clouds contribute a modest 20% global average greenhouse effect. If you include clouds and water vapor, you already know the intertwining of clouds and water vapor, that number increases to 66 to 85%. So these values here are kind of upper and lower bounds, depending how you calculate the effect. So it's kind of an upper and lower estimate on that. Let's first talk a little bit about what feedbacks are. I'm just going to give a couple of real-world examples, not at all pertinent to this lecture here, but negative feedbacks stabilize the system. You'll commonly hear them called as maintaining equilibrium or returning to equilibrium. An example is when we sweat on a hot day, it cools our body, and we bring our temperature back towards equilibrium. Positive feedbacks do the opposite. They destabilize. Some people call them a vicious cycle. An example of that would be the financial scheme of Bernie Madoff, where the payouts to the people at the top of the pyramid didn't come from any profit in the financial system. It was just from investments from people at the bottom of the pyramid. The thing collapsed with disastrous effects, as you've all heard in the news. An Earth climate example of a positive feedback is the ice albedo feedback. Imagine, as you understand, that ice has a high albedo. It reflects a large portion of the incident light. If the temperature warms and the ice melts, it's going to expose a dark surface underneath, either land or ocean. That dark surface means that there's comparatively less of that fraction of incident solar radiation escaping back to space, hence a warming, amplifying the effect. So that's an example of a positive feedback in the Earth climate system. Let's walk through only 2 cloud feedback examples. There are many. I don't understand lots of them. They're quite complex. And people really spend a lot of time trying to capture all the interrelations of clouds and their feedback effects so that they can better model the cloud effects of climate. But this is an example that I've already discussed in the talk. Say, for example, you have increased temperature. Leads to increased moisture in the atmosphere. You have more low-level clouds that reflect more of the incoming solar radiation, which decreases the energy or the temperature of the atmospheric system, inhibits this production here, bringing things back to equilibrium. Let's review positive cloud feedback example that I also discussed earlier. This is when you have increased temperature, perhaps you have increased upward air motions, increased high-level cloud, which tend to be thin, decreased reflection, more energy is reaching through to the atmospheric surface, which as increases temperature, amplifies the warming. So, where have I left you? If you follow the news on climate change, maybe you feel like this. And I can't tell you what the answer is, but maybe you'll rest easier at night knowing why. That clouds really are contributing to the largest uncertainties in the future climate change predictions by global climate models. So there we have it. We have more work to do. Let's talk a little bit about climate models and why we need them. I am not a climate modeler, so this is going to be my take on it, so it's pretty rudimentary. This is an example here of how they would represent Earth in a climate model as a 3D grid. Latitude, longitude grid cells with some vertical projection up from there. They're the most comprehensive tool for studying Earth's climate, and they're actually the only tool that can be used to predict effects on future climate by changes in things like greenhouse gases, cloud distribution, cloud cover, changes in surface albedo, etc. How they work is they solve some basic laws of physics, fluid motion, chemistry, at each one of these grid cells in here. I say, well, not entirely, because the climate models are really not at the point where they can model the complexity of the Earth climate system from basic first principles. And because of resolution and efficiency drawbacks, they use something they call tunable parameters. These are things they can kind of tweak a little bit to bring their model output more in line with what's observed. Your accuracy, of course, depends on the grid resolution and how well, of course, complex physical processes can be described by a mathematical equation. And they are tested by comparing their output with observations. Let's take a moment and do a little bit of a historical tour of not climate models as a whole, but just what's called the cloud feedback parameter from climate models over the last 25 years, say. What I mean by cloud feedback parameter is really a definition of the net cloud feedback to some radiative forcing that's been induced in the climate model. It's unitless. You can think of it as an amplifying factor of the direct radiative forcing. For example, so positive values are like the positive feedback. They're going to amplify the forcing. The negative values are like the negative feedback. They're going to actually bring things back to equilibrium. How this works, this is cloud feedback parameter versus 19 different climate models that participated in the study in 1990. And they set up a pretty simple experiment, and I'll try my best to describe it to you. Everyone induced climate change by making the sea surface temperature in the model 2 degrees warmer. They then kind of set things up so the only changes in albedo would come from cloud contributions and not snow or ice. And they really did that by restricting the latitudinal output that they looked in the looked at the grid outputs. They ignored the polar regions. They also held items like the soil moisture content consistent, so that there wasn't an addition or a change in the atmospheric moisture induced by soil-air interactions. They then do what they call spin up the model, let it run for a little time, and looked at the output. Since it's a model, they can clearly tell what is a cloudy grid cell and what's a clear grid cell. So they can simply look at the net radiative output as a function of cloudy versus clear and determine what portion was due to clouds or cloud feedbacks. And these are the results. So you can see very large disparity from amongst these 19 climate models, ranging from a few negative values to many positive values, and some very large positive values, which means this would be a large amplifying factor. A change in climate, cloud change due to a change in climate would really amplify the warming. So they realized they had some work to do. Everyone went back to the drawing boards and they repeated the same experiment in 1996. Same y-axis scale here. Red shading indicates models that participated in the 1990 study, and the ones that aren't shaded, I believe, are new entrants into the study. You can see that there's been a little bit more, they've definitely tuned in on the range of their possible outcomes from clouds and cloud feedbacks to some induced radiative forcing, but they're still really all over the board. Negative, positive, take your pick. Let's look again in 2005 when they repeated this experiment most recently. Here there's been a change in scale, and someone went ahead and ordered them so they look like a pretty pipe order. Red cells are, red shading is the models that have been in the study since the 1990 run, and the blue shaded ones have only been, they were involved in the 1996 and 2005 run. There has been an additional narrowing of the range of possible outputs, but they also discovered that even though they're maybe, I wouldn't say converging on a solution, they're far from that, they're not converging on a solution for the same reasons. So I talked about how there's this dual effect of clouds on climate, the albedo effect versus the greenhouse effect. They're not at all in line the change in magnitudes to those different processes. So that's kind of I know maybe a bit of a sobering analysis of a very difficult problem, which is the study of the radiative forcing from clouds and cloud feedbacks in a very complex interrelated system that is climate. So what do we know? This is a quote from Dr. Randall, Colorado State University. If you're interested, he gave a webcast. You can get it off the National Science Foundation website, and I can get that information for you after the talk. These are best current estimates of cloud feedback on global warming. That will be a moderate positive feedback with a significant uncertainty. And that this last part is very important to realize, because what that means is a moderate positive feedback could actually be a small negative or a cooling effect. It also could be a large positive effect. So where do we go from here? What do we need to do to improve our climate prediction capabilities, especially in relation to clouds, really in general, I would say. What we need is global, long-term, intensive satellite measurements of clouds. Any change in climate you would expect to be a very small signal over a very long period of time. So we have to improve the accuracy of the measurements, and of course we need the long-term measurements of them. This is an example of a cloud satellite retrieval from the MODIS instrument on board the Terra satellite. It just shows you how messy real-world clouds are. You would have a hard time separating into nice grid cells water clouds, low warm water clouds, from high cold ice clouds in this intertwined curving image here, which has some green vegetated signature from the surface underneath. Just a neat picture to look at. I'm getting short on time. Sorry about this. I'll go quick to the last part, which is what are my group's contributions to this? We don't make satellite measurements, so how can we contribute to this knowledge of clouds from air, sea, and land? I'll introduce here, this is just really briefly, this is our group. We do make measurements of radiance, and that's that watts per square meter people in the audience tonight, so thank you for coming up to support me. This is a very partial summary of our science focus. Really, this would be a whole nother seminar in itself. I'm just going to say that discuss clouds a lot entirely tonight, but there's other things like aerosols and surface albedo that are going to impact the transfer of energy in our atmosphere at ultraviolet through near infrared wavelengths, which is the wavelength range we measure over. So our measurements of clouds, aerosols, cloud and aerosol interactions, and surface albedo are all going towards ultimately refining and improving either the parameters that are used in the climate models or the satellite measurements that the climate models are comparing their output to determine their accuracy. And I wish I had more time. This is the instrument right here. It's called the Solar Spectral Flex Radiometer. I'm showing this here as such air, land, and sea just to emphasize that the climate system on Earth is complex and interrelated. So having the ability to measure energy from multiple locations and altitudes really enables us to better understand all the variables that are affecting clouds and their development. The satellite, of course, is really restricted, obviously, to one view of the system. I wanted to point out we do at times make measurements from the rooftop of the Duane Physics Building, not the Gamma Tower, but over in this region. This is a picture of the interesting aircraft called the Proteus from Scaled Composites. And this is one of the research vessels. We've been on several vessels from the Woods Hole Oceanographic Institution. Two quick science results from our group, which is not at all representative of all that we do, but I thought it would be interesting just to show you how we can contribute. Detecting biases in cloud properties. These are important because you want to make sure that what you're detecting is really correct. There's a field campaign off the northeast seaboard of the United States. The instrument was on a J-31 aircraft. It was really looking at pollution outflow over the Atlantic and its impacts on air quality and climate. What we found during the experiment is we came across a case where they were making measurements above a cloud, flying along this line, but we detected an aerosol layer above us. But that aerosol layer was not physically interacting with the cloud. We turned around and flew back along on an upper level leg above both cloud and aerosol. And the end result was that an absorbing aerosol layer, even though it's thin in comparison to a thick cloud deck, altered the upwelling radiance from that cloud top enough that it biased our cloud retrievals to a brighter and more reflective cloud. Obviously, a satellite has only one view of the scene, so that was kind of an important contribution that you can only make from aircraft. This is not a picture from that same science experiment, but it's illustrating a smoke plume above some clouds. And this was actually off the coast of Oregon and California after some forest fires. So not at all even in the same vicinity of the United States, but just gives you the general idea. Soot smoke tends to be an absorbing aerosol of the wide-ranging implications such biases could have in cloud properties. 2 slides left. Clouds from many perspectives. This is a field campaign, just from last year. And the reason why I wanted to show you it is that it's we have concurrent measurements of cloud from sea, aircraft, and space. So it's interesting to look how everyone's results combine together. As I mentioned, the SSFR was on no P3 aircraft and in a ship, an Atlantis ship. And the blue results here are the retrievals of cloud optical thickness, which I haven't defined, but you could really think of that as an extinction of light along a path due to the cloud along that path. And that's in the top plot here, optical thickness versus time. In the bottom plot, is an effective radius. This is not the same if you were to pluck a cloud drop out of there and measure it with your ruler. That's not the same measurement. This is an area weighted measure of the radius of that cloud droplet, the distribution of that cloud droplet. And so in blue again is the measurements from the ship. The orange line is measurements from GO satellite. And interspersed in here are some black dots, which is the aircraft measurements of the SSFR. There's one located there, probably resolution is not something you can see. And then the red stars are on that aircraft were also instruments that are meant to fly right into the cloud and measure the physical properties of that cloud, what we call it in situ. You can see that the comparison is really quite nice. But as in all things science, the most interesting and effective learning opportunities you're going to have is in regions where they differ. And I'll just basically leave it at that the regions where they differ are ongoing areas of scientific research for a multitude of reasons, and I don't have the time to go into them. The main impact that we were able to provide during this campaign was that this was the first time that the retrievals of these cloud properties were made from transmitted radiation. Typically, they're made from measurements above a cloud that's been reflected, the radiance has been reflected from the cloud top. This energy, for the blue curves here, has been transmitted through the cloud. That was the new retrieval